Hello, I'm Bill Kinney. This is video number 35 in my series on the foundations of arithmetic, algebra, and graphing. Part 4 of a sub-series on exponents, roots, and logarithms with an emphasis on calculator usage. I haven't really been talking about applications here because we need to focus on ideas. We'll get to applications of these things, especially to problems involving money. In the last video, we saw that well, I just said that it turns out to be a good idea to define any number besides 0 to the 0 power to equal 1. I didn't say why. I'll say why in this video. I wanted to do that to quickly give a reason for why 2 to the negative 1 power ultimately should equal 1 divided by 2 to the positive 1 power. And the reason I gave was based on an algebra kind of thing and based on a property of exponents that we want to be true. Now, this language I'm using of wanting something to be true and should equal might seem a little weird to you. These are not, these facts, these mathematical facts, for example, that 2 to the negative 1 equals 1/2 ultimately, are not true because we prove them to be true. They're true because we define them to be true, essentially. By saying should equal, I'm saying this is what I want 2 to the negative 1 to equal. I'm defining that equation to be true. Likewise, let's do another example. I'm defining an equation like this, 5 to the negative 1 to equal 1 over 5 to the first power by analogy here. This is not true because I'm proving it, it's true because I'm defining it to be true. In fact, any number b besides 0 to the negative 1 power is defined to be that 1 divided by that number b to the positive 1 power. In other words, just 1 over b, as long as b is not 0. It's a definition. The reason the definition is done is so that everything is consistent. So that, for example, 5 to the negative 1 times 5 to the positive 1 does in fact equal 5 to the 0, which is 1. And that's true because 1/5, that's equivalent to saying 1/5 times 5 is 1. 1/5 times 5 is 1. If we want this equation up here to be true, in other words, we should be able to add these exponents, negative 1 plus 1, to get 0 there, and ultimately get 1 at the end. Then we wanted to find 5 to the 0 to be 1, and we also want 5 to the negative 1 to mean 1/5, so that everything is consistent. Here's another reason why, for example, 5 to the 0 should be 1. 5 to the 0 times 5 to the 0, what should that be? Well, if our properties of exponents are going to be consistent, this should be the same as 5 to the 0 plus 0. Add the exponents. But what's 0 plus 0? It's 0. So 5 to the 0 should be a number with the property that when I multiply it times itself, when I square it, I get itself. Well, the only number that has that property is 1. 1 squared is 1. Therefore, 5 to the 0 should be defined to be 1. I know it's kind of a weird logic, but that really is the thought process that people go through in saying this is what we want to define raising to the 0 power to be, except in the case where the base is 0. That's undefined. And this is what we want raising to the negative 1 power should be. What about other negative powers, like negative 2 power? I'm realizing I'm low on paper here. Using the back of something here. Well, what should raising to the negative 2 power mean? Maybe I'm overusing 5 here. Let's try something else. 3 to the negative 2. What should that equal? Well, whatever it equals, if I want the properties of exponents to be consistent, when I multiply this by, for example, 3 to the positive 2, I should be able to add the exponents. This equation should be true. How should I define 3 to the negative 2 so that it is true? So that this does equal 3 to the 0, which is 1. Well, essentially you solve this equation for 3 to the negative 2, thinking of it as an unknown. I want to define what it is. Think of it in this equation as an unknown. Divide both sides of this equation by 3 to the positive 2. It divides out there. 3 to the negative 2 should equal 1 divided by 3 to the positive 2. And in fact it does, and that's the definition. That's going to be consistent with our previous definition of what 3 to the negative 1 power means. Think of that a couple ways. 3 to the negative 1 power squared. Well, what is 3 to the negative 1 power? It's 1/3. 1 over 3 to the first power. And what do I get when I square 1/3? I get 1 squared divided by 3 squared. I get 1 over 3 squared. Same thing as that. So indeed, these two things are equal. I can get from here to here by multiplying those exponents. Negative 1 times 2 is negative 2. Let's illustrate that another way. Let me reverse the roles of the negative 1 and the 2. What does this mean? 3 squared to the negative 1 power. What does that mean? Well, that's the same thing as 9 to the negative 1 power, because 3 squared is 9. 3 to the second power is 9. What's that? That should be the same as 1 over 9 to the first power, 1/9. Which is the same as that? Which is the same as this? 3 to the negative 2. Both of these, this and this, are both equal to that, and they both, with both of them, you can get from here to there or here to there by multiplying the exponents, negative 1 times 2 or 2 times negative 1. Either way you do it, you get negative 2. In general, if b is any non-zero number and I raise it to a negative power, I'll write it as negative m here. Realize that m itself would be positive. So like if this was negative 7, the m would be 7. That is equal to 1 divided by b to that positive power. All this stuff even works with irrational numbers. Pi is an irrational number. If I raise pi to the negative 3 power, it's the same as 1 over pi to the positive 3 power. Now, you might wonder, how do you even, here's sort of a subtle issue, how do you even define pi to the third power? How do you multiply pi times itself, really, if it's an irrational number whose decimal expansion goes on forever and ever? Calculator only gives you an approximation to it. How do you even multiply it times something? It's a little weird, you might wonder, how do you do that? Suffice it to say that it can be done. You might think of it in terms of successive approximations, getting better and better approximations to pi and using those to define the multiplication. But anyway, if I raise this to the negative 3 power, I get that. What's pi to the third power? It's that. Evidently, by what I just wrote over here, if I take 1 divided by that number, I need my second function key and then an answer button there. It's above the negative sign to get that A and S there to refer to the previous number. If I take 1 divided by that, that should equal the 0.0322515,344. It does. Now realize that these are, in reality, these are irrational numbers, all of them, and their decimal expansions go on forever and ever without a repeating pattern, but all this ends up being consistent, even with irrational numbers as the base. So I hope you're following this and thinking about it on your own. These are all important for solving real-life problems, especially in finance.